Welcome. My name is Brian McLogan, and I want to take you through our first day in pre-calculus dealing with functions. And today's lesson, we're going to discuss the characteristics of functions. And in this video, what I want to do is just kind of talk about the basic ideas of a function in our warm-up, kind of looking at, what kind of properties, how do kind of functions behave, what are some things that we can notice about a function, and then going through the definition of a function, how to determine if something is a function or not. Looking at function notation, and then investigating domain and range. So again, this is just going to give you kind of like the overview of functions and at least the characteristics, and how they behave and so on and so forth. So, in the warm-up, what I'm basically looking, what I ask is, given this graph, which is a function which we'll talk about, what are some things that we kind of, notice about this? Is the graph continuous? Is it broken? Does it go up? When does it go up? When does it go down? Does it have a max or min? Is there symmetry? And some other things. If the graph was expanded, where would it go? So let's kind of look at these individually and kind of see, just kind of write them informally, because we're going to learn the formal ways to write this, as we further get down through the course. So a couple things that I am noticing here, let's go ahead and use red, is the graph broken? You can see obviously at 0 here, the graph is from the left. Here we go to 3, and then it kind of jumps here down to 0, right? So it's not continuous. And the basic definition of, continuous is if you could draw this graph without having to lift up your pencil or pen. And you can see here I can't draw this. There's a little jump. So it is broken, and I can say it's, let's actually zoom in here. I'll say it is broken. Now, when we want to describe when something is broken, we want to kind of give some description, like where is it broken, right? So how can we describe where this graph is broken? We see that it's broken right here, but how can we tell that to somebody? And the best way that we're going to be characterizing characteristics with function is using the x values. So remember, of this graph, we could have an x and a y axis, right? So what we could say is, well, when x equals 0, the graph is broken. So I'm just going to say x equals 0. I'll just break that in there. It's when x is equal to 0. All right. So now let's go and take a look at another one. When does the graph going up? Well, we can see here, if we were to kind of think about this as like a roller coaster, you're riding this kind of graph here. If we start from the far left, you can see we're going down, and then it's going constant. And then as we jump, down in here, we're still going down, but it doesn't look like until when x equals 2, continuing, that it's going to start increasing. So we don't start going up until at 2, and then it looks like this arrow is going to continue on forever. So we can just say it is going up. I don't know what the y was there for. So let's just say up, at x, let's just say x is greater than or equal to, up when x is greater than or equal to 0. Or not 0, 2, right? Let's say, and then the next one, when does it stay the same? Well, it looks like it stays the same for all x values between -4 and 2, right? It's not going up or down at all. So I'm going to say constant. I'm having a hard time writing this. I guess I gotta zoom in. Constant. Let's see, what was that, from -4 is less than or equal to x, which is less than or equal to 0. And then we could say it's going down. And let's go ahead and look at again when it's going to be going down. So it's going down for our values that are going to be less than -4. So we could say when x is less than or equal to -4. And actually, you know what? It's not equal. At -4, it's not going down. So I'm actually not going to include that equal to sign. I'm actually going to rewrite those in there, because at those values, and you'll see that when we use our formal definitions, you'll see I don't use the included, because actually at that point it's not going up or down. That's actually a point in time. So it's going down from when x values are less than -2, and then it looks like, even though this is not defined and that one is defined, still at those coordinate points is actually not going down. So we'll just say, just use another comma here. And let's see, that's going to be from 0 to 2. So we'll say from 0 is, when x is greater than 2, but less than 2. All right, is there a max or a minimum height? Well, you can see these arrows are taking this graph up, so it looks like it's going to continue on forever, so there is not a maximum height. But you can see there is a minimum height, so we'll say no max. And we could say there is a minimum value at when x equals 2. And we could say of, what is that minimum value? It looks like -2. So we could say of y equals -2, right? And sometimes we'll write that as coordinate points, or sometimes we're just looking at the location of where it is, like the x value. The last one, or the next one, is it symmetrical? So is there like any lines of symmetry? Could I like draw a line that if we reflected it over vertically or horizontally, that we'd have the exact same graph? And you can see here there is really no symmetry of this graph. So I'm just going to write in no symmetry. All right, and let's see. As the graph continues, where would it go? So as we kind of follow this graph over to the left, you can see that the graph is going up, and it's going to continue going up. So the largest number, that it goes is, well, there is not a largest number, right? So we can say that as the graph is kind of continuing, it's going towards infinity. So we'll just say, let me just write that in there. So we can just say the graph continues to infinity, and I'll say left and right. So as the graph continues to the right, you guys can see that the graph is going to be continually going up towards positive infinity. As the graph continues to the left, it's going to continue going up towards positive infinity. All right, so that is basically a function, and what we're going to do is kind of look into the true definition of a function, which we, have talked about, something you should be familiar with, but it's really, really important for us to have a good understanding of a function. And a function, again, guys, is just a basic relationship between two variables, an independent and a dependent variable. And a lot of times we deal with x and y's, but again, it doesn't have to be an x and y. It can be z and Z and Q, as long as it is defined as what is the input and what is the output, or the independent and the dependent variable. So is it a function, a graph? So basically, to understand, when we're looking at a graph to see if something is a function, basically what we're just going to be doing is looking at what we just want to know is, passing the vertical line test. Okay, so you could have a function here, and let's do another function. Okay, so basically what the vertical line test is, because for it to be a function, maps to uniquely one dependent variable. So if my x values, right, here's my x-axis, every x value has to uniquely map to one y value. So we call this like the vertical line test. You can see that this x value, whatever this is, uniquely has one y value. So therefore that is a function. But if we look at the vertical line test of this graph, you can see this x value has two y values. So therefore it is not a function. So the best way to determine if a function, or the graph of a function, or the graph, is a function, is applying the vertical line test. And if that vertical line crosses the graph more than once, then it's not a function. As far as a table, we're kind of going to look at like the mapping kind of version of this. So, you could just have any kind of table here. X, Y, and I'm just going to choose. We covered this in the, preparing for pre-calculus. Let's just say -1, 2, let's say 3, 1, and let's do another one that is going to be the same, like, let's say 2, 2. Now again, what this works is this is still a function, because even if you wanted to plot this, even though they both go to 2, let's look at it. At -1 goes to 2, at 3 goes to 1, and at 2 goes to 2. So again, you can see that for each x value, we uniquely have one y value. So therefore, this is a function, even though it's not continuous like the previous examples. However, if I had a table, something like this here, where let's just do 3 to 5, let's do 2 to 1, and let's do 3 to -1. What you can see here is 3. Let's kind of use the same table so I don't have to redo it. In this example, you say 3 goes to 5, so 1, 2, 3, up to 5, 1, 2, 3, 4, 5. And then 3 also goes to -1, and then 2 goes to 1. So what you can see here is at the value when x equals 3, we have two y values. So therefore, the independent variable does not map to uniquely one dependent variable. So therefore, this is not a function. So I'm just going to say not a function. Not a function. Okay, now looking at an equation, and this is going to be primarily graphs and equations, primarily what we're going to be dealing with as far as understanding equations. Table is just kind of there for understanding, but we do talk about with the table. Now, when we're looking into an equation, basically, if you understand that this dependent variable has to come from, for each independent variable, we can only have one independent variable. So the best way to understand this is when solving equations implicitly and explicitly. So for instance, if I have the equation, let's just look at, x plus y equals 3. Okay. Now, this equation is implicitly solved, right? It doesn't solve for x or for y. So if I want to solve for y, right, I want to be able to know for each x value, am I going to get uniquely one y value out? I need to explicitly solve it for y. So to solve for y, I'm just going to subtract an x on both sides. So let's use orange. So I subtract an x on both sides. And now I get y equals negative x, I'll write that in front of the 3, plus 3, right? And you can see that for every value I plug in for x, I'm always going to get one y value out. And again, you can pick any number that you want to, or even graph it. And you'll see that every x value is going to spit out exactly one y value. Now, this changes, however, so the best way to be able to determine this, if you're given an equation, is try to solve for y. And as long as you can uniquely isolate the y, then you're going to have basically a function. So I can mess around with this by just doing this. If I had x plus y squared equals 3, follow the same process, right? Subtract an x, subtract an x. What was I using? Y blue? Oh, I want to use the dark. So now I have y squared equals negative x plus 3. And here comes our issue, because now to solve for y, I still have to do a second step. I have to take the square root, right? So now when I take the square root, check this out. I get y equals plus or minus, because you have to introduce a square root, you have to use plus or minus, negative x plus 3. So what happens is now I can't explicitly solve here for this y, because for each of these x's, now I have to take the plus and the minus. And what that does is that creates a graph that's going to look something like this, which is not going to pass the vertical line test. So the basic way to understand if something is a function is to be able to isolate the y, or to solve explicitly. And if you're able to do that, and you only have that, and therefore you're going to have that one term for x for every y, therefore it's a function. In this case here, you can see that I don't have one value of x, I have the plus and the minus version of it, so therefore it is not going to be an equation. Just a little FYI, that doesn't work if it looks like this. Like, let's say I have x squared plus y equals 3, then I have y equals negative x squared plus 3. And notice that's fine, right? You're still isolated for y, and for every value of x, I'm still going to get my one y. That's going to look something like this, so it's still going to be a function. All right, so understanding functions, it's fairly typical, something that I've covered before, but it's good to kind of run through. But the next kind of important thing is at least understanding function notation, and this usually gets students a lot when we're looking into understanding something as far as function notation. So, previously we've worked on examples of functions with like y equals, 3x plus 4. And we learned how to graph that, right? Finding your slope and, the y-intercept, so on and so forth. So the main important thing is when we're looking at that, we have a x-axis and we have a y-axis, right? For every x, you're going to plug in the x, for whatever value, plug in values in for x, and then you're going to get y. And that creates what we call a coordinate point. That's in terms of x and y. Okay? So function notation is really just replacing the value or replacing our notation for the output value. So what we'll use for function notation is, for instance, we'll say like f is a function of x equals 3x plus 4. So the easy way of doing this is just saying, don't really worry about it. Just replace y with f of x. Like, okay, yeah, it's fine. But what does really the f of x and the 3x plus 4 really kind of represent? So let's kind of break that down here. And I think I said, yeah, I did kind of call it. So in this example, 3x plus 4. Okay, so f is just the name. right? And we're going to look at another example of different name. Like sometimes we need to distinguish different functions from one another, and we won't know like the rule what it is. So we'll say call one like f of x, one g of x, whatever else. So the f is really just the way to differentiate our function. So that's going to be our kind of name. Inside the parentheses here, in this case is an x, is what we call our input. That is what we're basically plugging into the function. You can see here in the rule, it's 3x plus 4. It's, f of x. So it's the function of the input value x. And you can see here that the x is inside of the expression here. And that expression is actually what we'll call the rule. And that's the uniqueness, another uniqueness of functions. And that is going to be our rule. Okay, now the important thing about the rule is when you plug in a value in for x, so right now it's just a rule like 3 times x plus 4. But if I replace the x with like a number, then I'm going to get a value here, right? If I replace x with 1, then I'll have 3 times 1, which is 3 plus 4, which would be 7. So a lot of times this is also called the rule, but it's also the output value when x is defined. Okay, so when we have x as defined as some values, we also call it like the output. Now, again, we do not need to be stuck with f of x. Like f of x doesn't hold everything. Like we could also, if we wanted to, use this. What do I use? We could call this like g of a equals 3a. Oops, I don't know why I'm using parentheses. 3a plus 4. So what's important about this is when we're looking at this, now a is representing my independent value. So instead of this called the x-axis, we'd call this like the a-axis. Instead of this being the y-axis, we'd call this the g of a axis. And I forgot to do this one for the purple. When we replace y with f of x, we just use the y value as like our f of x axis. So it still represents, they all represent like the same area and location of the graphs. It's just different notation. And again, we would say like f of x equals 3x plus 4. And again, that's your input value. And whenever we want to find an input value, we, like for instance, or for what I was talking about, I guess I should say that. If I want to say f of 1, then what we do is we plug in the 1 in for the x plus 4. Sorry, kind of going backwards. And therefore that equals 7. So that is your output value, okay? And last but not least, let's go and take a look at the domain and range. So big thing about functions here is, obviously defining when we have a function, and then identifying the domain and range. And we're just going to look at like the basics of the domain and range in this example, just, nothing kind of crazy, because we know that when we have a domain, each x value uniquely maps to one y value. So sometimes we can deal with a function that is going to be, discrete, meaning it's not continuous. So, again, let's just, have some random numbers here. -1, 2, 2, 3, 0. I'll just pick 3 points, whatever. Again, the domain is the set of all x values, right? Or the set of all independent values, or the set of all input values. Really depends on, what type of function. A lot of times we use functions represented as an equation and with x and y's or with f of x. But again, guys, we could use, different names for this. So that's why it's important to understand the independent and the dependent values. Now, when we're dealing with a function that's like discrete, a lot of times using set notation is going to be kind of preferred. So I'll just write domain. And then I'm just going to list the values that are in my domain, or my x values, -1, 2, and 3. And the set is just a way for us to group all those values together collectively. And then I'll have the range, which I'll just write in ascending order, 0, 2, and 5. Okay, so the coordinate points, though, is rather easy because it's discrete. There's just, 1 point, then 1 point, then 1 point. But a graph, especially a continuous graph, is going to represent all the points, something where we could not write down every single point that's in the domain. So let's just kind of look at a basic graph here that is, I don't know, let's look at one that's, there we go. So here's the absolute value function, right? Now the domain, when you're looking at the graph, the way that I like to kind of understand this is by looking at the graph, we can basically say like the domain is the set of all x values. And you can see that there's a lot of x values every x value that I'm picking here has like a value on the graph, right? So I need some way to represent all these points that make up this graph, all these x values that make up this graph. And a way to kind of like, right, I can't list them all out. So what I'll do is I'll say, well, this graph is continuous. There's no like breaks or anything in it. So I can say, let's figure out how far left the graph goes to how far right it goes. And you can see as this graph expands to the left, it's going to keep on going. It's not really going to stop. So we can say that that graph going to the left is approaching negative infinity. So I'd write my domain. Now in this case, I'm going to use interval notation. Yeah, let's just, well, if we write it, let's write it in like set notation. So set notation, I could just say it represents like all real numbers. So I can say the set of all real numbers. Okay. I could also represent the set with like my kind of inequalities. So I could say the set from negative infinity, which is going to be less than or equal to x, which is less than or equal to infinity. But usually what is like the preferred way is using our interval. So basically saying like, what is the farthest point and what is the farthest point to the left and farthest point to the right. So the preferred method, which we'll be using mostly in this class, is going to be from negative infinity to infinity. And again, infinity, we're using parentheses here because infinity is not a number, so it's actually not defined. All right, for our range, range is a set of all y values, right? Well, you can see there's infinite many y values, but the interesting thing is there's no negative y values, right? There's nothing below the x-axis here. So my range is actually restricted at y equals 0. So a couple different, ways I could, say this. I could say it's basically all the values when x is greater than, when y is greater than 0. So I can say it's all y values greater than or equal to 0. Or in interval notation, I could say that the range is from 0. And then, so basically saying from interval notation, how low does the graph go to how high does the graph go? And you could say the lowest point this graph goes, or y coordinate this graph goes, is 0, and then it's going to go all the way to infinity. Now, my choice of using bracket here is because 0 is actually a point on, this graph. You can see there's actually a point at y equals 0. So therefore it is included in the range, whereas infinity is not a number, so therefore it's not included, and the graph continually goes all the way up. All right, so for an equation, we're going to get into this much more in depth in the next class period, so I don't really want to cover too much of it, but I think you guys kind of have a basic understanding of when something is defined or when it's not defined. So let's just kind of go through a couple examples. On an equation here, y equals x plus 3. Okay, so here's a function. Now, let's think about this. Is there any number I can plug in for x that is not going to spit out a y? You could think like negative numbers or like real numbers. No, like that's good. Like the domain for this one, there's no restrictions. There's no reason I can't plug in any number, at least in our real number system, that's going to give me an issue, right? So the domain here is going to be negative infinity to infinity, right? We're like looking good. That's all good. But now let's kind of play around with this. What if I put this in the denominator? Now it kind of gets a little interesting, right? Because now you think, well, what's the issue? Well, remember, the issue is, well, if we put in a -3 here, right? If I put in -3, then I'm going to have 1 over 0, and we can't divide by 0. So x equals -3 is an undefined term, right? It's undefined there. So I'm just going to write my domain as I'm going to use, we'll talk about set notation next class period later. So I'm just going to use my, here, I'm going to say it's all real numbers such that x cannot equal -3. Okay? And let's look at one more example. Y equals, what if I put it under a radical? So we know we can take the square root or the even root of all positive numbers, but what about negative numbers? Can we put the square root under any negative numbers? Well, no. So what number for x's then is going to make this negative? And whatever values are going to make that negative are not going to be in our domain because it's undefined. So you think about if I have like -3, well, -3 plus 3 is 0. Okay, that's good. But anything smaller than -3 is going to be make that radical negative. So therefore, that's not going to work. So my domain has to be all values that are greater than -3. So again, I'm just going to use my set notate or my interval notation for the or set notation, and we'll come back to identifying the. Oh, I guess I didn't think about that. Domain and range. Okay, we'll come over that. So the domain here is going to be all x values that are greater than or equal to -3. Now, as far as the range goes, we actually don't have enough information at this point to be able to find the range. We could think about that. We're going to show some steps of how to find the range. So just to give you an idea, if you're given an equation, you want to find the range, then for right now, you could plug these into Desmos or into your graphing technology, graph them, and then find the range that way. Otherwise, later this chapter, we'll learn how to find the range. So I'm actually going to have to not say find the range here because we'll find the range later in this chapter. So there you go, ladies and gentlemen. That's your examples for functions and their characteristics. Thanks.